How were the Houthis able to strike Israel from more than 1,000 miles away? The answer lies in their use of a combination of Iran-developed ballistic missiles and semi-hypersonic missiles, along with a special flight path known as a skip trajectory, meaning a trajectory that bounces along the atmosphere. But that raises an even bigger question. Why were these weapons able to get through Israel's advanced defense networks like Iron Dome and Arrow? The key is maneuverability. Unlike traditional ballistic missiles, which usually follow a predictable curved path, these newer weapons can change direction mid-flight, constantly adjusting their trajectory at extremely high speeds and making it very difficult for interceptor radar systems to track them all the way to the final phase. This was a shocking development amid ongoing regional tensions when the Houthis launched the missile they called Palestine II, a hypersonic ballistic weapon reportedly capable of reaching speeds of up to Mach 16. At that incredible speed, the missile could travel from Yemen to Israel in just minutes, leaving Israel's defense systems and those of its allies with very little time to react. What made this strike even more concerning was its ability to change course during flight, likely through a sophisticated skip-glide mechanism. That means instead of following a familiar and predictable arc, the missile could glide along the edge of the atmosphere, bounce in stages, and alter its path in ways that made interception far more difficult. Many experts believe this missile was not fully hypersonic in the classic sense, but instead had the characteristics of what might be called a semi-hypersonic design. Even so, its strong maneuvering capability during flight alone was enough to put it far beyond what older ballistic missiles could do. Mid-air trajectory changes like these create major problems for systems such as Israel's Aero-SEM or the U.S.'s developed aid, because those systems are designed to predict and intercept threats based on estimated flight paths. In everything, there has been speculation that the missile may have flown at a lower than usual altitude, allowing it to slip beneath radar coverage that is mainly optimized to detect high-altitude threats. This was the Houthi Palestine, used for the first time and believed to have been developed based on Iran's advanced missile systems. Inside this missile is a hypersonic glide vehicle that can detach from the booster stage and continue maneuvering and gliding at speeds ranging from Mach 5 to Mach 16. Its range is about 1,500 kilometers, only slightly greater than its predecessor Palestine I, also referred to as Fatah. What sets it apart from many other ballistic missiles is its ability to accelerate after leaving Earth's atmosphere, while its aerodynamic control surfaces allow it to steer and evade Israel's well-known Arrow missile defense system. The combination of extreme speed, sudden course changes, and a certain degree of stealth exposed a troubling vulnerability, even in one of the most heavily defended airspaces in the world. What this incident really shows is that non-state actors are now beginning to gain access to advanced weapons that were once considered the exclusive domain of major powers. The fact that Houthi militants in Yemen possess a missile with hypersonic characteristics represents a serious threat not only to Israel, but also to U.S. Navy warships. To understand how the Houthi hypersonic missile works, we first need to look at Iran's missile technology and Israel's Arrow system. The Houthis appear to be following the same strategy Iran used when it attacked Israel with nearly ballistic missiles. Those missiles traveled more than 10 miles from Iranian territory toward Israel's populated cities and military targets. In that recent attack, Iran is believed to have used variants of the Shahab-Sam ballistic missile. The Shahab-Sam is the foundation of Iran's entire family of medium-range ballistic missiles, uses liquid fuel, and can carry a warhead weighing from chilbeg yukshib to chon ibek kilograms, equivalent to about chon yukbek chushibo poundubato, I chon yukbek hashibo poundukachi. The way this missile works is fairly easy to understand. First, the missile is raised to a 90-degree angle and launched. Then, its ballistic trajectory carries it outside or close to the edge of Earth's atmosphere. Next, the warhead separates from the booster rocket that carried it upward. re-enters the atmosphere, and descends toward the target. Depending on the variant, the missile can carry one warhead or multiple warheads. Typically, the warhead separates from the single-stage rocket after the missile has traveled more than half the distance to its target. In the most common Scud variants, the circular error probable, or CEP, is around 300 to 450 meters. In other words, 80% of the missiles fired at a target would land within a circle of that diameter. That figure shows that the accuracy of older systems was still fairly limited compared with what is now appearing on the modern battlefield. At the same time, while you are following analysis like this, there is another issue worth paying attention to. Data broker companies may be collecting and selling your personal information, from your home address and phone number to your online search history, and even your financial data. That can lead not only to spam calls and scam attempts, but also to damage to your personal credit score if bad actors manipulate your data, potentially even causing a loan application to be denied. Some services, such as Incogni, also perform regular scans to keep your data from being put back on the market, while providing a real-time dashboard so you can monitor the status of your personal information. If you want to take back control of your data, solutions like that may be worth looking into. Returning to the main topic, Israel's defense system is built in 3 layers. The first layer is the long-range Arrow missile defense system, designed specifically to deal with threats from Iranian missiles. Each interceptor missile in this system costs several $1 million and can destroy targets outside the atmosphere, significantly increasing the level of protection. The second layer is David's Sling, which is designed to counter missiles and drones. Finally, there is Iron Dome, the well-known system responsible for intercepting most short-range rocket attacks aimed at Israel. So why was Iron Dome unable to stop Iran's ballistic missiles? In addition to looking at the entire layered defense network, Iron Dome itself only has a range of about 40 miles. David's Sling can intercept ballistic missiles at distances of up to about 180 miles. Meanwhile, the top layer, the Arrow anti-ballistic missile systems, can deal with threats from as far as 1,000 miles away. According to many reports, around Ballistic ballistic missiles, possibly with hypersonic characteristics as claimed by Iran's Revolutionary Guard, were launched. Although the Arrow system successfully intercepted many missiles before they reached Israeli territory, a significant number still got through. The biggest problem was that once the glide vehicle separated from the launcher or booster stage, it could change direction multiple times. Those constant changes disrupted the guidance process of the Arrow interceptors. That maneuverability also allowed it to get past David's Sling and, ultimately, Iron Dome, which was not designed to counter missiles with hypersonic characteristics like the Fatah II model. From a cost perspective, just one day of enduring and defending against missile attacks created a huge imbalance. Iran is believed to have spent more than Bekman Pala launching ballistic missiles and drones. Meanwhile, the Israel Defense Forces had to spend around Tala to defend themselves. That figure includes Arrow missiles at roughly $1,000,000 each, David's Sling at around $1,000,000 to produce, and Iron Dome at about $1,000,000 to $10,000 per interceptor missile, depending on inflation and price changes. By contrast, an Iranian ballistic missile cost only about $1,000,000, while its drones cost around $1,000,000 to $10,000 each. This is a confrontation in which the defending side has to spend far more than the attacking side. The Arrow defense system consists of 3 basic components: the missile launcher, the Green Fine Raider, and the Arrow missile itself. The runcher includes 6 uplight runch tube holding ready-to-fire missile mounted on the rear of a 2-axle trailer. When fully loaded with 6 ready-to-fire missiles, the entire launcher weighs about some ship 0 tons. The Green Pine radar serves as the early warning and fire control radar for the Arrow SUM anti-ballistic missile system and plays an extremely important role in detecting and guiding targets. The Arrow missile operates in a two-stage configuration. If you look inside this technology, you will see that the booster stage uses solid fuel rocket motors for both acceleration and sustained thrust. At the top of the rocket is the ignition chamber, where combustion of the solid propellant is triggered. This fuel is not a simple substance, but a carefully engineered mixture of fuel and oxidizer, poured into a casing and then cured into a solid form. Surrounding that mixture is a protective shell called the motor case. In the propellant burn zone, the solid fuel and oxidizer react with each other, producing extremely high-temperature gases that send the rocket racing upward beyond the atmosphere at tremendous speed. Moving farther forward, the most important part of the missile is the kill vehicle, or target destruction vehicle, and it can be divided into three basic sections. The second part is the propulsion system with a thrust vectoring nozzle.
Just about that is the directed high. 폭발성 fragmentation warhead, weighing 150kg, or about 330 pounds. The third part is the Seeker, which can pivot on its own tube, rack onto, and track the target. What is especially important in a long-range anti-ballistic missile system like this is that the ability to adjust its flight path in the final phase is absolutely critical. The well-known US THAAD system uses separate attitude control and divert thrusters. By contrast, the Arrow 3 kill vehicle uses a thrust vectoring nozzle, chimed with a solid fuel rocket motor. So its burn time is shorter and surmit more limited. Even so, it still has its own advantages. One of them is the ability to compensate for radar inaccuracy. When radar sends an interceptor toward a target location that is not fully accurate, the Arrow 3 kill vehicle can adjust its own trajectory. Because intercontinental ballistic missiles travel at extremely high speeds, the kill vehicle must constantly change course based on newer and more accurate radar data provided by its own seeker. If it fails to adjust its path fully toward the updated target position, the interception can fail. Overall, what makes attacks like these so concerning is not just the destructive power of the missiles, but also the fact that modern warfare is changing very quickly. Systems once seen as nearly impenetrable shields can now be challenged by weapons that are cheaper, more flexible, and harder to predict. And as that technology is no longer controlled exclusively by major powers, the risks to regional security, as well as to US forces operating in the area, will only continue to grow.